A fast Fourier transform is an algorithm to compute the discrete Fourier transform and its inverse. Fourier analysis converts time to frequency and vice versa. An FFT rapidly computes such transformations by factorizing the DFT matrix into a product of sparse factors. As a result, fast Fourier transforms are widely used for many applications in engineering, science, and mathematics. The basic ideas were popularized in 1965, but some FFTs had been previously known as early as 1805. Fast Fourier transforms have been described as the most important numerical algorithm, of our lifetime. Overview: there are many different FFT algorithms involving a wide range of mathematics, from simple complex number arithmetic to group theory and number theory. This article gives an overview of the available techniques and some of their general properties, while the specific algorithms are described in subsidiary articles linked below. The DFT is obtained by decomposing a sequence of values into components of different frequencies. This operation is useful in many fields, but computing it directly from the definition is often too slow to be practical. An FFT is a way to compute the same result more quickly, computing the DFT of n points in the naive way, using the definition, takes n2, arithmetical operations, while a FFT can compute the same DFT in only and log n, operations. The difference in speed can be enormous, especially for long data sets where n may be in the thousands or millions. In practice, the computation time can be reduced by several orders of magnitude in such cases, and the improvement is roughly proportional to n/log n. This huge improvement made the calculation of the DFT practical. FFTs are of great importance to a wide variety of applications, from digital signal processing and solving partial differential equations to algorithms for quick multiplication of large integers. The best-known FFT algorithms depend upon the factorization of n, but there are FFTs with now log n, complexity for all n, even for prime n. Many FFT algorithms only depend on the fact that is an nth primitive root of unity, and thus can be applied to analogous transforms over any finite field, such as number-theoretic transforms. Since the inverse DFT is the same as the DFT, but with the opposite sign in the exponent and a 1 per Newton factor, any FFT algorithm can easily be adapted for it. Definition and speed: an FFT computes the DFT and produces exactly the same result as evaluating the DFT definition directly. The most important difference is that an FFT is much faster. Let xn1 be complex numbers. The DFT is defined by the formula. Evaluating this definition directly requires n2 operations. There are n outputs xk, and each output requires a sum of n terms. An FFT is any method to compute the same results in and log n operations. More precisely, all known FFT algorithms require and log n operations, although there is no known proof that a lower complexity score is impossible. Johnson and Fourier, 2007, to illustrate the savings of an FFT, consider the count of complex multiplications and additions. Evaluating the DFT sums directly involves n2 complex multiplications and n1 complex additions, of which n operations can be saved by eliminating trivial operations such as multiplications by 1. The well-known radix 2 Coullier-Euro-Tukey algorithm, for n power of 2, can compute the same result with only log 2, n, complex multiplications and n log 2, n, complex additions. In practice, actual performance on modern computers is usually dominated by factors other than the speed of arithmetic operations, and the analysis is a complicated subject, but the overall improvement from n2 to and log n remains. Algorithms: Coullier-Euro-Tukey algorithm. By far the most commonly used FFT is the Coullier-Euro-Tukey algorithm. This is a divide-and-conquer algorithm that recursively breaks down a DFT of any composite size n equals n1 n2 into many smaller DFTs of sizes n1 and n2, along with n multiplications by complex roots of unity traditionally called twiddle factors. This method was popularized by a publication of J. W. Cooley and J. W. Tukey in 1965, but it was later discovered that those two authors had independently reinvented an algorithm known to Carl Friedrich Gauss around 1805. The best-known use of the Cooley-Tukey algorithm is to divide the transform into two pieces of size n/2 at each step, and is therefore limited to power of two sizes, but any factorization can be used in general. These are called the radix 2 and mixed radix cases, respectively. Although the basic idea is recursive, most traditional implementations rearrange the algorithm to avoid explicit recursion. Also, because the Cooley-Tukey algorithm breaks the DFT into smaller DFTs, it can be combined arbitrarily with any other algorithm for the DFT, such as those described below. Other FFT algorithms. There are other FFT algorithms distinct from Cooley-Tukey. Cornelius Lanczos did pioneering work on the FFS and FFT with G.C. Danielson. For n equals n1 n2 with k' n1 and n2, one can use the prime factor algorithm, based on the Chinese remainder theorem, to factorize the DFT similarly to Cooley-Tukey but without the twiddle factors. The Rader-Brenner algorithm is a Cooley-Tukey-like factorization but with purely imaginary twiddle factors, reducing multiplications at the cost of increased additions and reduced numerical stability. It was later superseded by the split radix variant of Cooley-Tukey. Algorithms that recursively factorize the DFT into smaller operations other than DFTs include the Bern and QFT algorithms. Bern's algorithm, in particular, is based on interpreting the FFT as a recursive factorization of the polynomial Z-1, here into real coefficient polynomials of the forms Z-1 and Z2m plus a Zm plus 1. Another polynomial viewpoint is exploited by the Winograd algorithm, which factorizes Z-1 into cyclotomic polynomials. These often have coefficients of 1, 0, or a 1, and therefore require few multiplications, so Winograd can be used to obtain minimal multiplication FFTs and is often used to find efficient algorithms for small factors. Indeed, Winograd showed that the DFT can be computed with only O(n) irrational multiplications, leading to a proven achievable lower bound on the number of multiplications for power of two sizes. Unfortunately, this comes at the cost of many more additions, a trade-off no longer favorable on modern processors with hardware multipliers. In particular, Winograd also makes use of the PFA as well as an algorithm by Rader for FFTs of prime sizes. Rader's algorithm, exploiting the existence of a generator for the multiplicative group modulo prime n, expresses a DFT of prime size n as a cyclic convolution of size n1, which can then be computed by a pair of ordinary FFTs via the convolution theorem. Another prime size FFT is due to L.I. Bluestein, and is sometimes called the Chirp-Z algorithm. It also re-expresses a DFT as a convolution, but this time of the same size, via the identity. FFT algorithms specialized for real and or symmetric data. In many applications, the input data for the DFT are purely real, in which case the outputs satisfy the symmetry. And efficient FFT algorithms have been designed for this situation. One approach consists of taking an ordinary algorithm and removing the redundant parts of the computation, saving roughly a factor of 2 in time and memory. Alternatively, it is possible to express an even-length real input DFT as a complex DFT of half the length, followed by O(n) post-processing operations. It was once believed that real input DFTs could be more efficiently computed by means of the discrete Hartley transform, but it was subsequently argued that a specialized real input DFT algorithm can typically be found that requires fewer operations than the corresponding DHT algorithm for the same number of inputs. Bern's algorithm is another method that was initially proposed to take advantage of real inputs, but it has not proved popular. There are further FFT specializations for the cases of real data that have even-odd symmetry, in which case one can gain another factor of 2 in time and memory and the DFT becomes the discrete cosine-sine transform, S. Instead of directly modifying an FFT algorithm for these cases, DCTs/DSTs can also be computed via FFTs of real data combined with O(n) Pre-post-processing. Computational issues, bounds on complexity and operation counts. A fundamental question of long-standing theoretical interest is to prove lower bounds on the complexity and exact operation counts of fast Fourier transforms, and many open problems remain. It is not even rigorously proved whether DFTs truly require a copyright, and log, n or greater, operations, even for the simple case of power of two sizes, although no algorithms with lower complexity are known. In particular, the count of arithmetic operations is usually the focus of such questions, although actual performance on modern-day computers is determined by many other factors such as cache or CPU pipeline optimization. Following pioneering work by Winograd, a tight I.N. lower bound is known for the number of real multiplications required by an FFT. It can be shown that only irrational real multiplications are required to compute a DFT of power of 2 length. Moreover, explicit algorithms that achieve this count are known. Unfortunately, these algorithms require too many additions to be practical, at least on modern computers with hardware multipliers. A tight lower bound is not known on the number of required additions, although lower bounds have been proved under some restrictive assumptions on the algorithms. In 1973, Morgenstern proved an I copyright, and log, and lower bound on the addition count for algorithms where the multiplicative constants have bounded magnitudes. Pan proved an I copyright, and log, and lower bound assuming a bound on a measure of the FFT algorithm's asynchronicity, but the generality of this assumption is unclear. For the case of power of 2n, Papadimitriou argued that the number of complex number additions achieved by Cooley-Tukey algorithms is optimal under certain assumptions on the graph of the algorithm. Thus far, no published FFT algorithm has achieved fewer than complex number additions for power of 2n. A third problem is to minimize the total number of real multiplications and additions, sometimes called the arithmetic complexity. Again, no tight lower bound has been proven. Since 1968, however, the lowest published count for power of 2n was long achieved by the split radix FFT algorithm, which requires real multiplications and additions for n greater than 1. This was recently reduced to. A slightly larger count was shown to be provably optimal for NA/per-mil 512 currency under additional restrictions on the possible algorithms, by reduction to a satisfiability modulo theories problem solvable by brute force. Most of the attempts to lower or prove the complexity of FFT algorithms have focused on the ordinary complex data case, because it is the simplest. However, complex data FFTs are so closely related to algorithms for related problems such as real data FFTs, discrete cosine transforms, discrete Hartley transforms, and so on, that any improvement in one of these would immediately lead to improvements in the others. Accuracy and approximations. All of the FFT algorithms discussed above compute the DFT exactly. A few FFT algorithms have been proposed, however, that compute the DFT approximately, with an error that can be made arbitrarily small at the expense of increased computations. Such algorithms trade the approximation error for increased speed or other properties. For example, an approximate FFT algorithm by Edelman al. achieves lower communication requirements for parallel computing with the help of a fast multipole method. A wavelet-based approximate FFT by Guo and Burrows takes sparse inputs-outputs into account more efficiently than is possible with an exact FFT. Another algorithm for approximate computation of a subset of the DFT outputs is due to Shentov al. The Edelman algorithm works equally well for sparse and non-sparse data, since it is based on the compressibility of the Fourier matrix itself rather than the compressibility of the data. Conversely, if the data are sparse, that is, if only k out of n Fourier coefficients are known 0 then the complexity can be reduced to O, clog, n, log, nk, and this has been demonstrated to lead to practical speedups compared to an ordinary FFT for nk greater than 32 in a large n example using a probabilistic approximate algorithm. Even the exact FFT algorithms have errors when finite precision floating point arithmetic is used, but these errors are typically quite small. Most FFT algorithms, for example Collier-Tukey, have excellent numerical properties as a consequence of the pairwise summation structure of the algorithms. The upper bound on the relative error for the Collier-Tukey algorithm is O(I) micron log n, compared to O(I) micron n3/2, for the Norvay DFT formula, where I micron is the machine floating point relative precision. In fact, the root mean square errors are much better than these upper bounds, being only O(I) micro-wash log n, for Collier-Tukey and O(I) micro-wash n, for the Norvay DFT. These results, however, are very sensitive to the accuracy of the twiddle factors used in the FFT, and it is not unusual for incautious FFT implementations to have much worse accuracy, for example if they use inaccurate trigonometric recurrence formulas. Some FFTs other than Collier-Tukey, such as the Rader-Brenner algorithm, are intrinsically less stable. In fixed-point arithmetic, the finite precision errors accumulated by FFT algorithms are worse, with RMS errors growing as O(n) for the Collier-Tukey algorithm. Moreover, even achieving this accuracy requires careful attention to scaling in order to minimize the loss of precision, and fixed-point FFT algorithms involve rescaling at each intermediate stage of decompositions like Collier-Tukey. To verify the correctness of an FFT implementation, rigorous guarantees can be obtained in O(n) log n time by a simple procedure checking the linearity, impulse response, and time shift properties of the transform on random inputs. Multidimensional FFTs, as defined in the multidimensional DFT article, the multidimensional DFT transforms an array Xn with a d-dimensional vector of indices by a set of d-nested summations, where the division Nn, defined as, is performed element-wise. Equivalently, it is the composition of a sequence of d sets of one-dimensional DFTs, performed along one dimension at a time. This compositional viewpoint immediately provides the simplest and most common multidimensional DFT algorithm, known as the row-column algorithm. That is, one simply performs a sequence of d one-dimensional FFTs. First you transform along the n one-dimension, then along the n two-dimension, and so on. This method is easily shown to have the usual O(n) log n complexity, whereas the total number of data points transformed. In particular, there are n1 transforms of size n1, etc., so the complexity of the sequence of FFTs is. In two dimensions, the xk can be viewed as a matrix, and this algorithm corresponds to first performing the FFT of all the rows, grouping the resulting transformed rows together as another matrix, and then performing the FFT on each of the columns of this second matrix, and similarly grouping the results into the final result matrix. In more than two dimensions, it is often advantageous for cache locality to group the dimensions recursively. For example, a three-dimensional FFT might first perform two-dimensional FFTs of each planar slice for each fixed n1, and then perform the one-dimensional FFTs along the n1 direction. More generally, an asymptotically optimal cache-oblivious algorithm consists of recursively dividing the dimensions into two groups and that are transformed recursively. Still, this remains a straightforward variation of the row-column algorithm that ultimately requires only a one-dimensional FFT algorithm as the base case, and still has O(n) log n complexity. Yet another variation is to perform matrix transpositions in between transforming subsequent dimensions, so that the transforms operate on contiguous data. This is especially important for out-of-core and distributed memory situations where accessing non-contiguous data is extremely time-consuming. There are other multidimensional FFT algorithms that are distinct from the row-column algorithm, although all of them have O(n) log n complexity. Perhaps the simplest non-row column FFT is the vector radix FFT algorithm, which is a generalization of the ordinary Collier-Tukey algorithm where one divides the transform dimensions by a vector of radices at each step. The simplest case of vector radix is where all of the radices are equal, but this is not necessary. Vector radix with only a single non-unit radix at a time, that is essentially a row-column algorithm. Other, more complicated, Methods include polynomial transform algorithms due to Nussbaumer, which view the transform in terms of convolutions and polynomial products. See Duhamel and Vetterli for more information and references. Other generalizations: NO, N5/2 log, N generalization to spherical harmonics on the sphere S2 with N2 nodes was described by Molenkamp, along with an algorithm conjectured to have O, N2 log 2, N complexity. Molenkamp also provides an implementation in the LIBFTSH library. A spherical harmonic algorithm with O, N2 log, N complexity is described by Rocklin and Tygart. The fast-folding algorithm is analogous to the FFT, except that it operates on a series of binned waveforms rather than a series of real or complex scalar values. Rotation is a circular shift of the component waveform. Various groups have also published FFT algorithms for non-equispace data, as reviewed in Potts et al. Such algorithms do not strictly compute the DFT, but rather some approximation thereof. More generally, there are various other methods of spectral estimation. See also, prime factor FFT algorithm, Bern's FFT algorithm, Radar's FFT algorithm, Bluestein's FFT algorithm, butterfly diagram. A diagram used to describe FFTs. Odlytsko paragraph NHAGE algorithm applies the FFT to finite Dirichlet series. Overlap add overlap save efficient convolution methods using FFT for long signals, spectral music, spectrum analyzers devices that perform an FFT, FFTW fastest Fourier transform in the WEC library for the discrete Fourier transform in one or more dimensions. FFTS, the fastest Fourier transform in the South. FTPAC another Fortran FFT library, time series. Math kernel library, fast Walshaw Hadamard transform, generalized distributive law, multidimensional transform, references, Charles van Loan, computational frameworks for the fast Fourier transform. Strang, Gilbert. Wavelets. American Scientist 82, 253. Retrieved October 8, 2013. Cooley, James W. Tukey, John W. An algorithm for the machine calculation of complex Fourier series. Math. Comput. 19, 297 301 doi, 10.1090 per second 0025-5718-1965-01785886-1 Hytham Hassan IA, Pyadrindak, Dina Katabi, and Eric Price. Simple and Practical Algorithm for Sparse Fourier Transform, ACM Siam Symposium on Discrete Algorithms, Kyoto, January 2012. See also the SFFT webpage. Brenner, N. Radar, C. A New Principle for Fast Fourier Transformation. IEEE Acoustics, Speech and Signal Processing 24, 264 266 doi, 10.1109/TASSP. 1976.116280 Brigham, E.O. The Fast Fourier Transform. New York, Prentice Haller, Thomas H. Corman, Charles E. Lesserson, Ronald L. Revest, and Clifford Stein, 2001. Introduction to Algorithms, 2nd ed. MIT Press and McGraw-Hill. ISBN 0-262-03293-7. Especially Chapter 30, Polynomials and the FFT. Duhamel, Pierre. Algorithms meeting the lower bounds on the multiplicative complexity of length DFTs and their connection with practical algorithms. IEEE Trans. Acoust. Speech. Sig. Proc 38, 1504 151 doi, 10.1109/29.600070 P. Duhamel and M. Vetterli, 1990, Fast Fourier Transforms, a tutorial review and a state-of-the-art, Signal Processing 19, 259 299. A. Edelman, P. McCorquodale, and S. Toledo, 1999, The Future Fast Fourier Transform. Siam J. Sci. Computing 20, 1094 euro 1114. D. F. Elliott, and K. R. Rao, 1982, Fast Transforms, Algorithms, Analyses, Applications. New York, Academic Press. Funder Ergo 1/4 n, 1995, Testing Multivariate Linear Functions, Overcoming the Generator Bottleneck, Proc 27th ACM's Symposium on the Theory of Computing, 407 euro 416. M. Frigo and S. G. Johnson, 2005, The Design and Implementation of FFTW3, Proceedings of the IEEE 93, 216 euro 231. Carl Friedrich Gauss, 1866. Theoria Interpolationis Methodo Nova Tractata, Worker Band 3, 265 euro 327. Gar Paragraph Tingen, Gar Paragraph Gesellschaft der Wissenschaften, W. M. Gentleman of G. Sand, 1966, Fast Fourier Transforms a Euro for Fun and Profit, Proc. AFIPS 29, 563 euro 578 doi, 10.1145/1,464,291.1464352, H. Guo and C. S. Burrus, 1996, Fast Approximate Fourier Transform by Wavelets Transform, Proc. SPIE Intel. SOC. Opt. Eng 2825, 250 euro 259. H. Guo, G. A. Sitten, C. S. Burrus, 1994, The Quick Discrete Fourier Transform, Proc. IEEE Conf. Acoust. Speech and Sig. Processing 3, 445 euro 448. Steve Haenel and Heidi Haenel, Generating and Searching Families of FFT Algorithms, Journal on Satisfiability, Boolean Modeling and Computation Volume 7, PPA 145 euro 187. Heidemann, M.T. Johnson, D.H. Burrus, C.S. Gauss and the History of the Fast Fourier Transform. UEASSP Magazine 1, 14 euro 21 doi, 10.1109/MASSP. 1984.11622257 Heidemann, Michael T. Burrus, C. Sidney. On the number of multiplications necessary to compute a length DFT. IEEE Trans. Acoust. Speech. Sig. Proc 34, 91 euro 95 doi, 10.1109/TASSP. 1986.116478 S. G. Johnson and M. Frigo, 2007. A modified split radix FFT with fewer arithmetic operations, IEEE Trans. Signal Processing 55, 111 euro 119. T. Lundy and J. Van Buskirk, 2007. A New Matrix Approach to Real FFTs and Convolutions of Length 2K, Computing 80, 23-45. Kent, Rodé and Reed, Charles. Acoustic Analysis of Speech. ISBN 0-7693-0112-6. Cite Strang, G. /Mile Euro June. Wavelets. American Scientist, 82, 250-255. Morgenstern, Jack. Note on a lower bound of the linear complexity of the fast Fourier transform. JACM 20, 305 euro 306 doi, 10.1145/321752.3217661 Molenkamp, MJA Fast Transform for Spherical Harmonics. J. Fourier Anal. APPL 5, 159 euro 184 doi, 10.1007/BF012616070 Nussbaumer, H. J. Digital Filtering Using Polynomial Transforms. Electronics Let 13, 386 euro 387 doi, 10.1049/L, 19,770,280 V. Pan, 1986, the trade-off between the additive complexity and the asynchronicity of linear and bilinear algorithms, Information Proc. Let 22, 11-14. Christos H. Papademetria, 1979, Optimality of the Fast Fourier Transform, JACM 26, 95-102. D. Potts, G. Steedle, and M. Tash, 2001. Fast Fourier Transforms for Non-Quiz-Based Data, a tutorial, in J. J. Benedetto and P. Ferreira, Modern Sampling Theory, Mathematics and Applications. Press, W. H. Tucholsky, S.A. Bettling, W. T. Flannery, B. P., Chapter 12. Fast Fourier Transform, Numerical Recipes, The Art of Scientific Computing, New York, Cambridge University Press, ISBN A978-0-521-88068-8. Rocklin, Vladimir. Tigert, Mark. Fast Algorithms for Spherical Harmonic Expansions. Siam J. Sci. Computing 27, 1903-1928. doi, 10.1137/05062307. James C. Schatzman, 1996, Accuracy of the Discrete Fourier Transform and the Fast Fourier Transform, Siam J. Sci. Comput. 17, 1150-1166. Shentov, O.V. Mitra, S.K. Hute, U. Hossan, A.N. Sub and DFT. I-Definition, Interpretations and Extensions. Signal Processing 41, 261-277 doi, 10.1016/0165-1684, 94, 00103-7. Sorensen, H.B. Jones, D.L. Heidman, M.T. Burrus, C.S. Real-Valued Fast Fourier Transform Algorithms. IEEE Trans. Acoust. Speech Sig. Processing 35, 849-863 doi, 10.1109/TASSP. 1987.11652220. See also Sorensen, H. Jones, D. Heidman, M. Burrus, C. Corrections to Real-Valued Fast Fourier Transform Algorithms. IEEE Transactions on Acoustics, Speech, and Signal Processing 35, 1353-1353. doi, 10.1109/TASSP. 1987.116528. Welch, Peter D. A Fixed-Point Fast Fourier Transform Error Analysis. IEEE Trans. Audio Electroacoustics 17, 151-157 doi, 10.1109/TAU. 1969.116203. Winograd, S. on Computing the Discrete Fourier Transform. Math. Computation 32, 175-199 doi, 10.1090 per second. 0025-5718-1978-04683006-4. JSTORA 2006266. External links, Fast Fourier Algorithm, Fast Fourier Transforms, Connections online book edited by C. Sidney Burrus, with chapters by C. Sidney Burrus, Ivan Selznick, Marcus Pueschel, Matteo Friego, and Stephen G. Johnson. Links to FFT code and information online. National Taiwan University FFT, FFT programming in C++ Coolio Tukey algorithm. Online documentation, links, book, and code. Using FFT to construct aggregate probability distributions, Sri Wellaratna, 30 Years of FFT Analyzers, Sound and Vibration. A historical review of hardware FFT devices. FFT Basics and Case Study using Multi-Instrument, FFT Textbook Notes, PPTs, videos at Holistic Numerical Methods Institute. Alglib FFT Code GPL licensed multilanguage numerical analysis and data processing library. MIT's SFFT MIT sparse FFT algorithm and implementation. VB6 FFT VB6 optimized library implementation with source code.